God bless. So that was it for chapter 10. And so now we're going to talk through chapter 11 a little bit, which is about developing strategies for addition and subtraction computation. According to the Common Core State Standards, students should solve addition and subtraction problems with numbers appropriate to their grade level. So for kindergarten, that would be up to 10, within 100 for first grade, and then within 1,000 for second grade. Addition and subtraction strategies that build on decomposing and composing numbers in flexible ways contribute to students' overall number sense. These methods can be done mentally and are faster and easier than standard algorithms. Now, if you don't feel equipped with a lot of strategies, that's okay. We're going to look at several through this video that will help you with that. And you'll notice that place value, like we talked about just a few minutes ago, is important to emphasize as computation is being taught to truly deepen and enrich students' numeracy understanding. The figure that you see on this slide lists a general instructional sequence that includes 3 types of computational strategies. The first is direct modeling, the direct modeling method. And this can, with guidance, develop into an assortment of more flexible and useful invented strategies, which are here now in the middle. That's the second stage. And we'll talk about these in depth a little bit later, but they are exactly what they sound like. Student invented strategies. Students come up with their own ways to make sense of these different computations. And then lastly are the standard algorithms. And these are important for students to learn too. This is probably the way that you and I learned addition and subtraction when we were younger, right? Lining up the 2 digits, right? And then borrowing if you need to with subtraction, etc. Now, I think where the problem lies is that oftentimes teachers don't go through the first 2 stages, right? These do happen in a sequence. Teachers kind of skip over the first 2 stages of the sequence and then go right to standard algorithms, which again, the standard algorithm in and of itself is not bad, but when a teacher is only using the standard algorithm to teach, it's more so promoting memorization of the procedure rather than real understanding of what we're doing to add or subtract 2 numbers together. Direct modeling is the first technique that you want to demonstrate to students and which they in turn will employ to solve problems. Direct modeling is the use of manipulatives or drawings along with counting to directly represent the meaning of an operation or story problem. So the figures on the slide here, they show 2 instances of 36 plus 27 in the first one, and then 47 plus 36. So now students who consistently count by ones need support to develop base 10 grouping concepts, just like we talked about in the last chapter. The goal is to move them from direct modeling to invented strategies derived from number sense and the properties of operations. So that's where I want them to move, but this is still a good place to start, right? So if you gave your students a problem like 36 plus 27, right? Well, then they can model 36 first, and then they model 27, and then they can consider all of that together. Now, here are a few tips to promote the fading of direct modeling. So you can ask students who have just solved a problem with models if they can do it mentally. You can also ask them to put into writing how they solved with a model and ask them to replicate the method on a new problem. And so just helping them transition out of direct modeling into the next phase. Now, this next phase is the invented strategies. An invented strategy is any strategy that does not involve a standard algorithm or the use of physical materials or counting by ones. And so at times, invented strategies become mental methods. When I like to think of them as just ways to do mental math. So for instance, a student may be able to do 75 plus 19 because 75 plus 20 is 95, and then just take one less to get to 94. For instance, some students may also need to write down the intermediate steps to do 847 plus 256. So one of the best ways for students to grow their repertoire is to listen to the strategies invented by classmates as they are shared, explored, and tried out by others. So these invented strategies, again, just not the standard algorithm, and they do have these 3 characteristics. They are place value oriented rather than digit oriented. In the standard algorithm, right, we have 45 plus 32, and this students think of 4 plus 3 instead of 40 plus 30. So the invented strategy anchors on that idea of place value, right? That the 4 represents 4 tens, the 3 represents 3 tens, so altogether we would have 7 tens. We know that they are left-handed rather than right-handed. So, for example, in the standard algorithm, they're right-handed, meaning the students start by adding the ones, then they move to the tens, then they move to the hundreds, etc. However, in the invented strategy, students begin on the left. So they're starting with the biggest units, the hundreds, and then they can add the tens, and then they can add the ones. So this does have more of a focus on the whole number and some sense of size of the eventual answer rather than looking at each digit individually. And then also the invented strategies, they give a range of flexible options rather than just one right way. Now, there are a lot of benefits of these invented strategies. The first is that students make fewer errors, right? Because they're understanding why the standard algorithm works, or they're understanding how the numbers truly add together instead of just memorizing. In that sense, then there will be less reteaching required. And at the same time, it does help your students grow in their number sense. Invented strategies are also the basis for mental computation and estimation. Again, just the ability to do mental math and not relying on a calculator. And then these flexible methods are often faster than the traditional algorithm. And then it does serve students well on standardized tests, right? Just to be quicker. And again, especially if one section of the test is a no calculator part, right? They have the ability to do that small computation in their mind rather than relying on a calculator. So here, continue on with invented strategies. There are a few pedagogical methods or things that we can do as teachers that support the development of these invented strategies. First is to avoid immediately identifying the right answer when one student states it. It's important that you give others a chance to share their thoughts too, as they might be coming up with a different invented strategy that might also get to the right answer. You should expect and encourage student to student interactions, questions, discussions, and conjectures, right? Helping understanding that the students will learn from each other. You should encourage students to clarify and connect to their previous knowledge. You should also promote curiosity and an openness to trying new things, especially with these invented strategies. And talking about right and wrong ideas in a non-evaluative or non-threatening way, which is what you guys talked a little bit about in the lab, right? Allowing a mistake to go through, but using it as a learning experience. And then moving unsophisticated ideas to more sophisticated thinking through coaching and strategic questioning. Again, our stages of questioning that you guys knew for the test. Using familiar context and story problems to build background and to connect to students' experiences, and then showing samples of anonymous students' work and allowing students to critique the reasoning. So all of these are good ways for us to help our students develop invented strategies. Okay, so the Common Core state standards have the development of fluency with multi-digit addition and subtraction beginning in grade 1, with the addition of multiples of 10 and continuing through 4th grade, when students are expected to fluently use the standard algorithm. So they have to know how to use that standard algorithm by 4th grade, or through the end of 4th grade. So on the slide here, we're going to look through four different invented strategies. And each of these responds to the following story problem. 2 scout troops went on a field trip. There are 46 Girl Scouts and 38 Boy Scouts. How many scouts went on the trip? So our first example of an invented strategy here is to add the tens, add the ones, and then combine. So for 46 plus 38, you would add 40 and 30 to get 70, and then you would add 6 and 8 to get 14, and then you would add 70 to 14 to get 84. I will say that this is a very effective strategy, and I actually use it with my high school kids all the time. Instead of having them take out their calculators, I will often have them add the tens and then add the ones and then combine the result. The next strategy is the add on tens and then add ones. So here we say that 46 and 30 more is 76. Then I added on the other 8. And so 76 and 4 is 80, and 4 is 84. And so there, right, again, we started with that 46, and then we kind of added that 30 more to get to 76. Then we added on the other 8. But to add on that other 8, we broke it down into 2 4s, because 4 got me to 80, but then that 4 more got me to 84. The next strategy is move some to make tens. And so here you're kind of just taking units from one number and bringing them to the other. So here we take 2 from the 46 and put it with a 38 to make 40. But since we took 2 from the 46, we now have 44. So 44 and 40 more, though, is 84. Right, so borrowing to make a full group of 10. And then the last strategy on this slide is to use a nice number and compensate. So 46 and 40, right, because 38 is really close to 40. 46 and 40 is 86, but I had 2 extra, so I take away 2 to get to 84. Now on this slide, there are a few invented strategies for subtraction. Honestly, I think the best way for our students to think about subtraction is that think addition way. It's a very good strategy, a good way to teach multi-digit subtraction. So here are 3 varied approaches for 73 students were on the playground, 46 second graders came in. How many students were on the playground? So the first strategy here for this subtraction is to add tens to get close and then ones. So for 73 minus 46, and this here is that think addition strategy. So 46 and 20 is 66. If I added 30 more, that would be too much because that would get to 76. And then from 66, 4 more gets me to 70, and then 3 more is 73. So 20 plus 7 is 27. So I got there by starting at the smaller number and then thinking through addition until I got to the bigger number. The next strategy is to add tens to overshoot and then come back. So 46 and 30 is 76. That got me the closest to that 73 number while going a little bit over, but that's 3 too much, and so I take away 3 from the 30 that I added to get 27. And then another strategy is to add ones to make a 10, and then tens and ones. So 46, I start at 46 again, thinking addition. I add 4 to get to 50. And then using benchmark numbers from 50, if I add 20 more, I get to 70. And then I add 3 more to get to 73. So 4 and 3 is 7, and then add that to 20 to get 27. So here are 4 more subtraction strategies that involve taking away or jumping back. So here's same problem though, 73 minus 46. So in the first one is to take tens from the tens and then subtract the ones. So 70 minus 40 is 30. Take away 6 more is 24. And now add in the 3 ones to get to 27. Another strategy here is take away the tens, then the ones. So 73 minus 40 is 33. Then take away the 6. 3 makes 30. And then if you take 3 more from that 6, you get to 27. The next one is to take extra tens then to add back. So 73 take away 50, which is too much, gets you to 23, and that's 4 too many. So 23 and 4 is 27, right? So adding that back. And then the last way is to add the whole if necessary. So give 3 to 73 to make it 76, and then 76 take away 46 is 30, and now give back that 3. So 30 from 30, giving back the 3 would get you to 27. So all these different strategies, again, these are all just invented strategies, different ways that students could think of these problems. But for subtraction, you can either think addition or go through the thought process strictly with subtraction. So now on to the standard algorithms. And a way to transition your students to these is to encourage them to record their process, not only as they model with base 10 maths, but also as they kind of think through these invented strategies. And as you have your students model and record the process, that you can help them through these guided questions, which you see here on the screen. And this really does help them transition from the invented strategy to the standard algorithm. And so here, you could ask things like, how much is in the ones column? And then, will you need to make a trade? Yes. And then how many tens will you make? 1. How many ones will be left over? 4. Good, then make the trade now. And then have them stop there and then record what they're doing. And you can see how this does really nicely translate to that standard algorithm. Now, we also have a standard algorithm for subtraction, as you know. The general approach to developing the subtraction algorithm is the same for addition. So you can have your students modeling a problem while also writing, beginning with those models, and then asking probing questions in a similar way that you did for the addition. Now here, again, we know that it's important to address misconceptions, so it's important that you anticipate difficulties with zeros. And then it's also important that we're continuing to encourage our students to develop that written record. One last topic here is estimation. We talked about estimation when it came to number sense. Remember, I had that yellow footprint cut out in class. And estimation, it's really important. Again, we talked about how it connects them, helps them connect to real life, and helps them develop their number sense. But it's also a quick way for our students to produce an approximate result that will work for the situation, right? Remember, estimation really does link to number sense. And so there are 3 types of estimation. There's measurement, which is where students determine and approximate measure, right? There's quantity, which is approximating the number of items in a collection. And then there's computational, which is determining a number that is an approximation of a computation. So let's talk about some general principles here with estimation. So it's important that you use real examples like shopping, distance to travel, monthly budgets, cost of entertainment like sporting events, movies, etc. It's also important that you use the language of estimation, words like about, close, or just about, a little more, or a little less than, or between. It's important that you use context to help determine the reasonableness of the estimate. For example, would attendance at a school play be 30, 300, or 3,000? And since it's estimation, we're not looking for an exact answer, so it's important that you accept and offer a range of estimates as an option, that you accept multiple strategies, and that you focus on flexible methods and not necessarily strict answers. So there is one common technique to help our students with this computation estimation. It's called the front end method. And so the leftmost number is used, and computation is then done as if there were zeros in the other position. So here is an example. So it's front end addition in column form. So here we're estimating the adding of 489 plus 37 plus 651 plus 208. And so here, instead of going through that whole problem, we're just thinking about that leftmost number. So 4 plus 6 plus 2 is 12. But since that's in the hundreds place, that's about 12,000. But if we consider the hundreds place, 835, we make that adjustment to about 150 more, so that gets us to about 1350. And then there's another example here of front end addition. So if we're adding 398 to 4,250 to 2,725, again, we just consider that leftmost number, which is in the thousands place. So 0 plus 4 plus 2 is 6, and that's about 6,000. And then we make our adjustment based on the hundreds place. So 3 plus 2 plus 7 is 12. So then we add about 1,200 or 1,300 more to get us to about 7,300. Now, there's a second method here that we can use to help our students with these estimation problems, and this is the rounding method. And so here, numbers can be rounded to the same place value for addition. And here, rounding is very important, and so is the concept of compatibility, where the differences or the compatibility of numbers, the differences are based on a multiple of 10. So in the rounding method, numbers can be rounded to the same place value for addition, as we said. And so, for example, what is the appropriate value of this coin collection? So 4,827 is really close to 5,000. 710 is really close to 1,000. And then in the grand scheme of things, 85 is pretty close to 0. So if we're rounding to the thousands, 5,000 plus 0 plus 1,000 is about 6,000. And then we have our compatible numbers, which is kind of taking advantage of those benchmark ideas where we change the values of numbers so that they fit together a little bit better, right? Again, basing that on multiples of 10. So I can change 128 to 124, and then from 124 to 184 is 60, right? So lots of different strategies here to help our students with estimation. So that's it for chapters 10 and 11. Again, be on the lookout for my email or reference my email from earlier this week for the other things you should be doing. And as always, feel free to reach out at any point with any questions. God bless.